In this short video, we'll look at error constants. Now, the motivation. Error constants provide additional information beyond what we can get from system type. Uh, they allow you to quantify steady state characteristic of a system. Essentially, what you can do is with error constants, you can easily calculate the steady state error for systems that are in unity feedback for various inputs. So what do I mean by unity feedback systems? The sensor has no dynamics, therefore h, which is in the feedback path, equal to 1. Types of error constants, there are three, namely position error constant k subscript POS associated with system type 0, velocity error constant k subscript vel associated with system type 1, and you guessed it right, acceleration error constant KACC associated with system type 2. Position error constant, it's associated with system type 0. System type 0 implies that non-zero implies a non-zero constant steady state error for step input. So let's do that. What I have done here is just multiplied the transfer function of the plant and controller to get the single transfer function g dash, and that is in unity feedback. We get an expression for error like so. If you have step input, r of t is a times step. A is the amplitude of the step. Therefore, the Laplace transform of this function is a divided by s. Substitute that in the previous equation, you get this error equation. Then you find what the steady state error is. Steady state error is a limit as s tends to 0, s times e of s. We substitute for e of s. Now this s cancels with this s, and you can write ESS is essentially a divided by 1 plus limit as s tends to 0 g dash. Now limit of s tends to 0 of g dash is k subscript POS, the position error constant. Therefore you can write steady state error ESS is a divided by 1 plus k position. Velocity error constant is associated with step, system type 1. What that means is the system gives you non-zero constant steady state error for ramp input. Just like before we do the unity feedback system, write an expression for error. Now if r of t, the reference input in the time domain, is a ramp with amplitude a, the Laplace transform of this function is a divided by s squared. Substitute that in the error equation and write an expression for steady state error like so. So this s cancels with one of this s, and you multiply the remaining s with the denominator to get this. Now as s tends to 0, this s becomes 0, so you end up with this. Notice that this is not 0 because you can typically separate out 1 divided by s from g dash, and that 1 divided by s cancels with this s, and therefore this is a non-zero constant. Therefore the steady you can now write the velocity error constant as limit s tends to 0 of s times g dash. Therefore the error is given by a divided by the velocity error constant. Similarly, the acceleration error constant is associated with system of type 2. System type 2 implies that you get a non-zero constant steady state error for parabola input. Same as before, write an expression for the error. If you have parabola input, the Laplace transform of that is a divided by s cubed, where is the amplitude. Substitute that in the error equation, find an expression for steady state error like so. One of this s cubes gets cancelled with this s, multiply the remaining s squared through here, this should be s squared, and therefore you can write steady state error ESS is a divided by limit as s tends to 0 s squared g dash. Now if the system is of type 2, you can factorize 1 divided by s squared from g dash, therefore that s squared will cancel with the factorized 1 by divided by s squared. So this term in fact is going to be a non-zero constant. Therefore, the acceleration error constant k subscript acc is equal to limit as s tends to 0 s squared g dash. Therefore, the steady state error ess is a divided by the acceleration constant. Now, to summarize, you can see this table right here. So if you have system type 0 and you send it a step input, your steady state error ess is given by a divided by 1 plus k position. This should be pos. The steady state, so this is a non-zero constant. K position, the position error constant is a constant as well. Obviously, you know from before, for system type of 0, if you give a ramp input, you're going to get infinity steady state error. That means the velocity error constant is 0. Same thing with parabola, and so on and so forth. Like I said before, for system of type 0, g dash equal to s to the power of 0 times g alpha, where g alpha, so s to the power of 0 is 1, and g alpha is a rational function of s where you cannot separate out any power of s. System type 1, you can write g dash is equal to g alpha divided by s. That's what I meant, that g dash you can separate out, factor out a 1 divided by s from g dash. And for system type 2, you'll be able to factor out a s squared from g dash. So g alpha is again a rational function of s from which you cannot factorize an s squared. That's the end of our lecture.